memory for embedded system. If you recall, we discussed the embedded system in our previous lessons, and which basically the embedded system actually uses a microprocessor or microcontroller, which basically has a number of input, output, serial port, memory types, which is like ROM, RAM, and so on then, and is used in applications such as microwaves, dishwashers, washing machine, vending machine, and so on then. So what we're going to do is that basically we have a look at the information on the type of the memory we can actually use for embedded system. So if you look at in here, the summary of this lesson is going to be basically the memory for embedded system, address decoding, memory function types, memory hardware types, static RAM, dynamic RAM, and basically non-volatile memory and direct memory access. Normally what we have is for embedded system, basically it's got the challenges are memory management. So basically the size of the on-chip memory is limited. As you can see, for example, for application of a mobile phone, if you've got a mobile phone for various applications and whatever, you're always basically limited to amount of memory you've actually got, and it's the same for computer. So the same application applies for embedded system. So the size of the on-chip memory is normally limited, and it's basically you can actually expand certain type of memory using external devices and so on then. So basically what we have is that we've got to basically embedded system that you can actually use to limit the amount of memory you have, and then don't basically limit the amount of the applications and so on. And normally, because the application, the type of the application, you shouldn't need to have large amount of data and so on then. So what we have is that basically we've got to have a way of finding to actually address the memory. If you remember, we had on a microprocessor, microcontroller, we basically have a data bus and address bus. So the address bus, basically, if you remember, every memory location has got a unique address, and you've got to be able to actually access these addresses and so on. Then you should be able to actually read or write to this location. For example, if you've got in here as an example, depends on the number of bits you've got. For example, if you've got 10 bits or 10 address line, which is 2 to the power of 10, because that's based on binary, so we've got 1024 basically bits of memory. So that's which is equivalent to about 1K. So you can actually access 1K of memory location. So what happens if you actually increase this one to, say, for example, 11 lines? So if you go to 11 lines, that will be 2 to the power of 11. That will give you 2K. If you go again to 12 lines, that will give you 4K. So it will go up with a multiple of 2. So that will be 1K, 2K, 4K, 8K, 16K, 32K, 64K, and gradually goes up and so on then. So basically, this is what you've got. And then you can actually have, for example, a memory location that you can actually use and so on then. So for example, let's look at this one in here. We need 8 memory location chips. So if you actually use different ICs, basically that's 8 times 128, that's 1024. And then we need basically to have 3 address lines to select each one of these chip. Okay, so we can actually use 3 address line to select each one of these one to actually then access the memory. So if you look at this one, the addressing one, the address decoding, so what you've got in here, you've got CPU, and the CPU basically provides the address and the data bus. in here we are not basically, the data bus is not showing, but we've actually got the address bus. So if you look at this one, we've got basically 3 to 8, for example, address decoder. So it will take 3 inputs. So 3 inputs, basically 2 to the power of 3 in binary number, is basically gives you 8 different combination, which will be 0 to 7 and so on. So if you actually have these 3 bits, normally they actually use it as a top of the address bus, which is the most significant bits and so on then. So you've got 3 address bits coming in here, and then that divides to basically 8 different combinations. So each one of these one is called chip select. So you've got chip select, for example, 0, chip select 1, chip select 2, chip select 3, and it goes up to chip select 7. So each basically time you want to actually access a memory location, what you need, these 3 bits, they set up which memory location you would like to access. And then basically once you've actually set up the actual, decide on the chip and the memory locations and whatever, then you've got the address decoding. So the addresses will be set up for that chip select device and the memory address, memory location you've actually decided and so on. So what you need to do, you set up the actual, you select the chip and then you set up the address to access the memory locations and so on. So what we're going to do is that basically we're going to look at the memory type that we can actually have in here and so on then. So the memory type is basically any memory, is basically any data register is just a small element of memory embedded in CPU. A distinction of memory types can be made according to their functionality and so on then. So for example, working register. Now these are basically what they are. They are inside the CPU and extensively used with the assembly language. For example, if you actually write program in C, C++, that will be normally converted to assembler by the compiler, and it actually uses the working register inside the CPU. For example, if you actually look at PIC32 microprocessor, it's got 32 working register or internal register that's basically used for all sort of application. For example, you can actually use, some of them is used for stack pointer. It's basically, you can actually access the information and so on then. So basically these are the actual working register, and depends on the microprocessor. Each the microprocessor has got different number of working register that you can actually use. So it's a temporary storage values of the CPU, which basically uses and so on then. Now, if you look at this one, then you've got the data memory. For basically for longer term storage, generally CPU usually basically they use external, they employ external memory, which is larger than any onboard memory. So the microprocessor, microcontroller, normally they've got some basically onboard memory, and then if you need more of them, you can actually have or add external memory. So this one you can actually then use that one for any data or larger applications and so on then. Also what you have in here, so that's the data memory. To basically, you can actually attach external memory to CPU, which basically requires some hardware effort and so on. Then, however, a lot of microcontrollers, they should have sufficient onboard memory. Then you've got instruction memory. So basically, the instruction memory, this normally is large or whatever, and this one, you can actually use it. This is your for microprocessor instead of microcontroller. And these are normally holds the actual program itself. So this is the actual instruction memory, which is basically you actually use it for your program and the applications and so on. Also, we've got other type of the memory you can actually use, and the function of it that basically can be used depending on the CPU and whether it can be used with the pipeline, register, cache, and various things and so on. So if you look at this one in here, on the actual memory hardware types. So if you look at the memory hardware types in here, you've got, based on the way that basically the memory is used. So what you've got is hardware or chip designer usually view the memory rather than in a different way and so on then. And basically depends what's the actual physical properties of the actual electronic part of the actual memory and how it's actually done and so on then. Now we can actually look at the two different types of memory. Normally is called volatile versus non-volatile memory. So in volatile memory, the content of the memory is basically lost as soon as the system power is switched off. So basically as soon as you switch something off and switch it back in, that's it, all the information is lost. However, with the non-volatile memory, this information is actually retained, and you can actually recover the information. For example, if you've got mobile phone, you turn the power off and on, you still actually remember, the phone remember all this configuration and the network and the data and so on then. So these are basically, you've got volatile and non-volatile memory. So basically if you actually look at this one in here, so look at this one in here, different type of the memories. So you've got semiconductors, basically that's the memories are made of, and in here you've got volatile one. So the volatile one could be like static RAM. It could be dynamic RAM. Dynamic RAM normally is much cheaper than the static RAM, but you've got to update it at regular interval. Then you've got EEPROM. Basically you've got ROM, you've got PROM, EEPROM, EEPROM, flash, and non-volatile RAM. So these are basically what you've got, is that the memory types that of the hardware you can actually get and use and so on them. So basically what you've got, as mentioned basically above, the volatile memory retains its content, so you can actually keep all the informations or whatever, and when the system basically powers up and so on them. So basically you've got to decide whether you need a volatile and non-volatile. With a volatile one you loses it, and with non-volatile one you actually keep the informations and so on them. So basically you can actually use this information for, depends on the type of the applications and so on you'll be using. Look at this one in here. For example, we have a static RAM. Now the static RAM is basically, it consists of an array of cells, each capable of storing 1 bit of information. And this one, for example, you can actually store 1 bit of information, and this one, if you actually you've done flip-flop, is very similar to that one. So basically if you flip-flop, you actually remember, so you can program it to remember what the information is and so on. So basically if you look at it on a static RAM, you've got, normally these are the input, data in, you've got data out, you've got read write. Normally it's basically simplified by read stroke write, and normally 1 is, for example, for reading and a 0 for writing. And this one, CS, is chip select. So basically when you've got a lot of memory ICs and whatever, the microprocessor uses the address decoding to actually select the correct IC before it actually reads or writes to it. So this is the static RAM. And if you look at the static RAM, for example, in here, as you say, data in, so basically that it will accept the information. Data out is that basically is whatever is you actually trying to read from the information. Read write is basically whether you are writing or reading information to the actual device, and static RAM. And chip select is basically selecting the memory and ICs and so on then. So these are the main configuration of a memory type that you could actually have for a static RAM. Non-volatile memory is virtually similar, exactly that basically you keep the actual information and so on. And so that's the difference between volatile and non-volatile. Now then you've got another type of the memory, and this type is ROM. So basically what the ROM is that read-only memory. So read-only memory is that basically normally is your program, so the application software and so on. Then when you actually develop software, normally you actually put it in this type of memory. So it's a read-only memory, and you can actually use it for mass productions and so on. Then. So this is used for mass productions and so on. Then, and make sure that if you're writing your software, the application is fully debugged. Otherwise, you program a lot of these ROMs, and you suddenly realize there is a bug in it. Then you've got basically non-volatile. You've got PROM. So the PROM is that basically is the same as the what is called is a ROM. What it is programmable read-only memory. So basically they are exactly the same as the other one, but you could actually program these devices and so on. Then. So these are sometimes you could actually have one-time programmable microcontrollers and so on. Then. So basically you can actually only program it once and so on. Then. All right. So PROMs and one-time programmable microcontrollers are not suitable for development, because don't forget, if you're doing development, you've got to actually keep testing your software and debugging it and rewrite everything and so on. Then. So these are not suitable for actual development and so on. Then. And these are only suitable for the actual full production. So EEPROM, then we've got another type, which is EEPROM. That's erasable programmable read-only memory. So it allows up to basically change the memory content of the IC, and basically what it is using some sort of field effect transistor to actually do it. So by applying an appropriate high voltage, you need to actually have a high voltage in order to actually program this device, and that will be programmed and you actually use it and so on. Then. So this is normally used for actually using configuration informations and so on. Then. So this is how you actually use EEPROMs and so on. Then. Okay, so that's EEPROM that you can actually have. Then you can actually have, it will have various charges and so on. Then. So what it does is that basically you've got to be careful with the EEPROM. Over time, the floating gate loses enough electrons to become unprogrammed. So these are basically what you do when you charge it. It will actually hold all the electrons in the actual floating gates and so on. Then, but after the time and whatever, so it depends on the time. Some of them they go up to about 10 years and so on. Then they gradually loses their charge and so on. Then, so that will be unprogrammed and unusable. Okay, so what you do, you could actually have EEPROM. In order to actually reprogram it, you've got programmable devices, and you can actually put it under ultraviolet light and for 30 minutes and so on. Then you can also erase it that way. So it will erase it, and once you've erased it, then you can actually reprogram it again and put it into the actual your embedded system. Normally this was used in old technology, that basically you would put a socket for this EEPROM, and then you would program it, and it had a window on the top as well. So then basically you will test and debug your software. If you didn't like it, you'll take it out. Obviously there was a bug in the software. You take it out, put it in one of these ultraviolet light boxes for half an hour, and basically erase the program and then reprogram it. And that was extremely tedious and very long way of basically inefficient way of debugging and testing your software. Now, if you've noticed now with the latest technology we are using, and the MX20 board basically is all used with flash. If there is a bug in the program, you can immediately reprogram it without taking anything out and so on. Then. So the technology is moved on, and everything is much faster and more efficient and so on. Then. Now we've got in here EEPROM, or basically electrically erasable programmable read-only memory, has the advantage of the EEPROM, but basically you don't need to have no special voltage is required for programming. So no more ultraviolet light source is needed for erasing. So this one is that basically what you could do, you can actually do it electronically in your circuit. So you can actually apply some small voltage like 3 or 5 volts or whatever, and then you can actually reprogram it. And normally this EEPROM are basically in a serial format, and you can actually program it for all the configuration and various information. One of the application, for example, could be like car radio. If you've got a car radio, you can actually store all the various stations like BBC One, BBC Two, and so on. Then, and when you switch off your radio, and then each time you switch it on, it will basically recover the information what you've actually programmed into your radio. And these are basically one of the applications that you can actually use for EEPROM and so on. Then. And basically the last one of the non-volatile memory is flash. As you've heard, that basically flash is a variant of basically EEPROM, that basically erasing is not possible for each address. So you can't actually erase it for each address. You've got to actually erase the whole lot. And normally all the latest technology, for example, MX20 board has got about 512K of flash, on board flash. So that is basically used for your program, which was like the old technology. It was equivalent to ROM, read-only memory. So with this flash, you basically erase everything. You basically reprogram your program in there, and then you actually run it and so on. Then, and with the sum of the actual, if you're clever enough and so on, then with the flash use on MX20, you could actually use up to about 1 or 2K of the flash out of this 512 as EEPROM. So basically you could actually store some configuration information, so whenever you actually then even you reprogram and whatever, it will remember the configuration, how you can actually configure your systems and so on then on various applications. So basically that's it. So we looked at all the type of the memory for the actual embedded system, and we can actually then basically look at it in here. Just to recoup, these are the memory hardware types that we actually have for embedded system. Normally you've got basically semiconductor devices. It's volatile, non-volatile. Volatile is basically it will changes, and normally a static RAM. We've got a static RAM and dynamic RAM. And non-volatile, you've got basically it doesn't change. That will be ROM, PROM, EEPROM, EEPROM, flash, and non-volatile RAM, and so on. So these are the type of the memories actually used for embedded system. Thank you.